All right, so today we're going to cover the last three here. So we talked about the equilibrium constant K. We learned the difference between Kc and Kp. We learned a little bit about how to calculate the equilibrium constant K. And today we're learning about a few more things. The reaction coefficient or reaction quotient, which helps you predict which direction the reaction will go. Is it going towards the products, or is it going towards the reactants? And then we're going to look at calculating more equilibrium constants, and finally LuciaToliss Principle. All right, so first let's talk about the reaction quotient. Again, as I mentioned earlier, you can determine reaction quotient and predict which direction the reaction will go, right? So if a reaction mixture is not at equilibrium, how can we determine from which direction the reaction will reach equilibrium? So that's when reaction quotient comes into play. So in order to do that, in order to predict the direction of the reaction, you have to determine the QC, right, or reaction quotient, and compare that with the value of Kc. So basically, you'll be given the value of Kc. So you would have to determine QC and then compare it to Kc. Okay. So QC, the reaction quotient, is the concentration, the initial concentration ratio, which is similar to Kc. So the expression, right, the reaction quotient expression is similar to that of the equilibrium constant. The only difference is you're using initial concentrations and not concentration at equilibrium. So let's look at this typical reaction equation for gas phase reaction. You have the reactants A and B turning into products C and D. So you would express the reaction quotient similar to what you would do normally for Kc. Right, so it looks something like this. So you have the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Okay, so QC then is the reaction quotient in terms of concentration, and QP is the reaction quotient in terms of partial pressures. So as you can see, it's the same expression as Kc. Now, again, the only difference is you're using initial concentrations here and not equilibrium concentration. All right, so how do we predict the direction of the reaction, right? So again, you would have to compare the value of Q with the equilibrium constant K. So first here, if the reaction quotient K is greater than K, the equilibrium constant K, the reaction will proceed fastest in the reverse direction. So what that means is that the reactants are actually favored here. Okay? It also means that the product concentration is greater than the reactant concentration. So the change has to go from right to left, right? From the products to the reactants. Okay, again, if Q is greater than K, that means that the product concentration is a lot greater than the reactant concentration. And so that also means that you're already way past the equilibrium. But if Q is less than K, then the reaction will proceed fastest in the forward direction, right? Forward meaning going towards the products. So in this case, products are favored. And if Q is less than K, then that means that the concentration of the reactants is greater than the concentration of the products. Okay. So the concentration of the products will increase over time, and the concentration of reactants will decrease over time. And the last comparison here is if Q is equivalent to K, then the reaction is at equilibrium, and so neither the product nor the reactants are favored. Okay, so you have the same basically rate of reaction between the forward reaction and the reverse reaction. All right, so this slide right here basically illustrates the direction of a reaction and how that's related to Q and K. So, for example, if we have this general reaction equation here, you would have the reaction quotient expression shown here, right? So it's the concentration of the product divided by concentration of reactants. And so if you're given the values of the reactants and the products and plug it in here, you'll see that Q actually approaches infinity if the concentration of A is close to 0, right? So if you plug that in, then the value of Q approaches infinity. So what that means is that Q is a lot greater than K. And so if that's the case, the reactants are favored, right? So you're way past that equilibrium state. And so the reaction would go from right to left towards the reactants. So that's what's shown here, right? In order to restore that equilibrium, the reaction has to go from right to left towards the reactants. All right, but if Q is less than K, then you haven't reached that equilibrium yet, right? You don't have enough products compared to the reactants, and so the reaction has to go forward towards the products to make more products, and so the reaction goes from left to right. Okay, it shifts to the right. But if your reaction quotient is already equivalent to the equilibrium, then the product nor the reactant is favored. All right, let's look at an example here. Consider the reaction, and it gives you this chemical reaction equation with the known value of Kp. Okay, and so whenever you're setting up your equation, you would want to compare the value of Qc, the reaction, or the Qp in this case, the reaction quotient, and Kp, the equilibrium constant. So your Qp then, right, the reaction quotient in terms of partial pressure is equivalent to the partial pressure of ICL raised to the second power, right, divided by the partial pressure of the reactants raised to their coefficients. Okay, and you're given the initial concentrations here, and so you can just plug in the numbers. Did you have a question, Eric? All right, so you just plug in the initial concentrations here. So you have partial pressure of ICL, which is 0.355. You square that, divided by concentrations of the reactants, which is 0.114 times 0.102. Okay, so plug that into the calculator. And we get 10.8. So similar to the equilibrium constant, there's no unit for reaction quotient, right? So you can see that compared to Kp, Kp is a lot larger, right? So your Qp is less than Kp. So that means that you don't have enough products, right, compared to the reactants. So which direction do you think the reaction will go? Forward, right, towards the products. So reaction proceeds forward. Okay, this also means that the products are favored. Okay, so the question here is the reaction mixture at equilibrium? Well, because Qp is not equal to Kp, it's not at equilibrium. And we just determined that the reaction goes forward. All right. So how do we find the equilibrium concentration if you were given the value of K and all the other equilibrium concentrations or pressures? So let's look at this chemical reaction equation. If you have 2 moles of COF2 breaking down into carbon dioxide and tetrafluorocarbon, it gives you the Kc value here. And it also gives you the concentrations at equilibrium. Right, so it says over here equilibrium mixture. This is the concentration of COF2, and this is the concentration of CF4. Okay. Question is, what is the equilibrium concentration of CO2? So at this point, you don't need to compare QC and KC. Right, you just need to determine the expression for Kc. So we know Kc is equivalent to concentration of CF4 raised to the first power times the concentration of CO2 raised to the first power divided by the concentration of the reactant raised to the second power. Okay, and you're already given the value of Kc, right? We know that value. We know COF2. We know CF4, but we don't know what CO2 is. This is what we're trying to find here. So you can treat that as your X, right? So treat them badly. Get it? Your X? Okay. All right, so we isolate CO2 by itself. Kc times COF2 squared divided by CF4, concentration of CF4. All right, so Kc is 2.00 multiplied by COF2 concentration squared divided by concentration of CF4, which is 0.118. And we get 1.10. So this is the concentration of CO2. So that example is a little bit easier. It's more straightforward. So here's a cleaner version, 1.10. All right, so that one is simple because you're given all the concentrations at equilibrium, including the Kc. All right, so what if you're only given the initial concentrations and the value of Kc? Then you would have to determine the equilibrium concentrations. All right. So here's an example. All right. So finding equilibrium concentrations when you're only given K and the initial concentrations. You would have to follow these 4 steps. You already know the first step. You know how to prepare the ice table. The second step here is actually very important. Okay. So you have to compare the value of Q with K. Okay. Because that will tell you which direction the reaction will go. Which, is it the products that will receive the positive X? Is it the reactants that will receive the negative X? Right? So comparing Q and K will let you decide which direction the reaction will go. So step number 3, define the changes of all substances in terms of X. Okay? And we use the coefficient from the chemical equation as the coefficient of X. So for example, if you have 2 CO2 in the product, then you would use 2X for the change when you have that ice table. That change in concentration would be 2X for CO2. Okay? The X change is negative for materials on the side the reaction is proceeding away from, and positive for substances on the side the reaction is proceeding towards. Right? So for example, if the products are favored, then the products will receive that positive sign. Okay? If the reactants are favored, meaning it's going the reverse direction, then the reactants will receive the positive sign. And then step 4, you just solve for x. Okay, so you plug in the functions that you determined for the equilibrium concentration onto the equilibrium constant expression. So let's look at an example here, because this is a lot of words. So let's put this into action. All right, so again, consider this reaction equation here, A turning into B. Notice that B has a coefficient of 2, right? And you're given the initial concentrations, but not equilibrium concentrations. And you're also given the value of Kc. So what you would do is prepare your ice table, right? Okay, so you have initial concentration here, change in concentration, and then E for equilibrium concentration. And then we have two things. We have the reactant A and the product B. And you go ahead and put the 2 there to remind you that you're supposed to multiply that by 2. All right, so we're given the initial concentrations. Initial concentration of A is 1.00. Concentration of B is 0. And we know the Kc here. All right, so that was step 1. Step 2, you compare the value of Qc and Kc and see which direction the reaction will go. All right, so for Qc expression, that would be B squared divided by A. Okay, and we're given the value of B here, so that's 0 squared divided by 1.0, which is essentially 0. So Qc, as you can see here, is less than Kc. Right, our Kc value is 0.33. So that means we haven't reached equilibrium yet, and so the reaction will proceed towards the products, right? It'll go forward. So reaction moves forward. So it means the products will receive a positive sign, right? All right, so we can go ahead and start putting x, right? So for change, for C here, the product will receive 2x because of the coefficient 2. So this will receive positive 2x, and then the reactant will receive negative x. Okay, and then your equilibrium then for reactant A will be 1.00 minus x. So you just do the math here. It's like playing Sudoku, you just fill in the blank, right? 0 plus 2x for this one. And there goes your equations for the equilibrium. So now we know that the Qc expression is actually similar to the Kc expression, right? The only difference is we're plugging in the equilibrium concentrations. So now our Kc then is equivalent to 2x squared divided by the concentration of A at equilibrium, which is 1 minus x. And this is equivalent to Kc, which is 0.33. Okay, and then you can just simplify this and you get a quadratic equation, right? So that would be 4x squared equals 0.33 times 1 minus x. Okay, so 4x squared.
Why is it 4x squared?
Because you're squaring the 2x. Right, so right here.
Oh, okay.
Yeah. All right, so 4x squared equals 0.33 minus 0.33x. Okay, you guys follow that? So I basically multiplied 0.33 and 1 minus x, and then simplified it. And then you can make this equation equal to 0, right? So 4x squared plus 0.33x minus 0.33 equals 0. So that's your quadratic equation, and you can use the quadratic formula to determine x. Do you guys remember the quadratic equation? What is it?
X equals negative b plus or minus the square root of b squared minus 4ac all over 2a.
Divided by 2a. So that's something that we learned from high school, right? The teacher made us memorize it. So make sure you know that equation, because I don't think it's in the formula sheet. And if you have a graphic calculator, you can also just graph it and determine x. All right, so you use that equation, you get the value of x. Okay, so a cleaner version. So we use this quadratic formula to determine x. So once you get that x value, right? So let's say that the x value that you calculated was 0.25. Okay, so this is just an example. So let's say the calculated x was 0.25, then you plug it into the equilibrium function, right? So that would be 1 minus 0.25, then you get 0.75 is the concentration of the reactant. 2 times 0.25, then you get 0.5 for the concentration of the product. Okay. All right, let's look at an actual example here. So again, you're given the initial concentrations of the reactants. You're also given the Kc value here. Okay, so how do we determine the equilibrium concentrations of the reactants and products? So first thing you want to do is set up your ice table. All right, so ICE here. And we're given the concentrations of nitrogen gas and oxygen gas. So that's 0.2 here. And also 0.2 for oxygen gas. And we're going to have to assume that the initial concentration of the product is 0. Okay, because we're making the product. All right, and then you compare the value of QC and Kc. So the expression for QC then is equal to the concentration of the products raised to the second power divided by concentration of the reactants raised to the first power. Okay, and you're given the initial concentrations here. So we have 0 for the product divided by 0.2 times 0.2, which is essentially 0 for QC. So QC then is less than Kc. So because you haven't reached the equilibrium yet, the reaction moves forward. All right, so we've determined that the reaction moves forward. That means that the products will receive the positive sign, positive x. So in this case, we have 2 here, so that's plus 2x, minus x, and also minus x for nitrogen gas. All right, and then you do the math, you have 0.2 minus x, same thing over here, 0.200 minus x. And the last one is 2x. All right. And QC expression is the same as Kc expression. So Kc equals the concentration of nitrogen monoxide. So that's 2x squared divided by 0.200 minus x for nitrogen gas times 0.200 minus x for the oxygen gas. So you can simplify this equation. Okay, wait. So Kc is equal to 0.10, so I'm going to go ahead and put that over here. And then simplify this equation, 4x squared divided by 0.200 minus x squared. All right, because these two right here are the same. Okay, and we can simplify this further by taking the square root of both sides. All right, so we'll take the square root of this and the right-hand side. And now we have 2x divided by 0.200 minus x and we get 0.316 here. Okay, and then you can simplify this and get a, not even a quadratic equation here. Let's see, so 2x equals, so I'm going to use this space over here. So 2x equals 0.0634 minus 0.06, that's not right, 0.316. X. All right, and then you can isolate x to one side. So 2x plus 0.316 is 2.316x. That equals 0.0634. And then x by itself is equivalent to...
How did you get the 0.0634?
Let's see. It's 0.316 times 0.2. So x here is 0.027. Okay. So now that we've determined the constant, the value of x, we can plug this into the equations over here. Right, so 0.2 minus 0.027. And so the concentration of nitrogen gas at equilibrium is 0.17. Okay, we can do the same thing here for oxygen gas. It would be the same. And then 2 times 0.027 is 0.054. So these are the concentrations at equilibrium. Question, Eric?
Should it be 0.13?
0.13 for which one?
Equal for the equilibrium concentration? The first two?
The first two? Well, isn't it 0.2 minus 0.027?
Okay, so
Did I plug that in incorrectly? 0.173.
oh yeah, just okay.
All right, do you guys have any questions?
Does it have a unit?
It would be in molarity because it's concentration. All right, so this is basically the answer here. All right, I think there's another example here. Let's see. All right. Okay, so this one is probably a little bit simpler compared to the previous one. All right, consider this reaction. You're again give the value of Kc, and you're also given the reaction mixture concentrations. Find the equilibrium concentrations of both the reactant and the products. All right, so let's work on this together. Again, the first thing you want to do is prepare an ice table. All right, so we have N2O4 and NO2 here. And we're given the initial concentration of nitrogen monoxide, which is 0.1. And here we're going to have to assume that the initial concentration of dinitrogen tetroxide is 0. And then we set up the expression for QC, which is the reaction quotient. So we have concentration of NO2 to the second power divided by concentration of N2O4. And so if you do that, we have 0.100 squared divided by a value close to 0. And so you can assume that QC approaches infinity when the reactant is close to 0. All right, so QC then is greater than the value of KC. So the reaction will proceed in reverse. All right, so that means that the reactants will get the positive sign, right? So that would be plus X here, and then the products will receive the negative sign, so minus 2X in this case. And then the equilibrium concentration equations would be 0.100 minus 2X for the product, and then X for the reactant. And then we know that QC expression is the same as KC. Okay, and then we just plug in, so KC is equivalent to 0.36, and that's equivalent to the concentration of nitrogen dioxide squared, which is 0.100 minus 2X squared divided by X. Okay, and then we simplify this, so we have 0.36, X equals 0.100 minus 2X squared. And then at this point, you would have to do the FOIL, right? You've heard of FOIL. First outside, inside, and then last. So when you do that, you get 0.36x equals 4x squared minus 0.4x plus 0.01. And then you can just make this quadratic equation equal to 0. So 4x squared minus 0.76x plus 0.01 equals 0. So now we have the coefficients here. Our coefficients are A equals 4, B equals negative 0.76, and C is 0.01. So you can plug this into the quadratic formula, and when you do that, you'll get two values of x. Okay, you'll have x1 and x2. So the x1 here is 0.176, and the other x value is 0.0143. So sometimes you'll get one negative and the other one is positive. So obviously the positive one will be the right answer here. But in case of two positives here, then you would have to plug this into the equilibrium equations and see which one will be the one that will give you a positive outcome, right? And so if you look at the concentration of nitrogen dioxide here, if you were to subtract 0.100 minus, let's say, 2 times 0.176, that would give you a negative number, right? Because x is greater than 0.1. Okay, so in that case, x1 here will not be the right answer. So you would use the second value of x, 0.0143. So instead, 0.100 minus 2 times 0.0143. And we get 0.072. All right, so this would be the concentration of the reactants, and then the concentration of the product, and the concentration of the reactant would be 0.0143. Okay, again, so this is for N2O4, and this other one is for NO2. All right, I think there's another example here in which it gives you the partial pressures, initial partial pressures, and you have to determine the equilibrium partial pressures. All right, so here's one. Again, you're given the Kp value. You're also given the initial concentrations of the products and the reactants. Okay, find the equilibrium partial pressures of all the chemicals involved. All right, so it's the same idea here. Okay, so you're going to prepare your ice table. So we have I2, Cl2, and 2ICl. And you're given the initial concentrations. So we have, or initial partial pressures, 0.100 for all of them. So now you can't really tell which direction the reaction will go, right? Because they all contain partial pressures. Okay, so you would have to compare QP and KP. So the expression for QP then is equivalent to partial pressure of ICl squared divided by partial pressure of the reactants. Again, this is the same expression as Kp. All right, so we plug in numbers for Qp. You can see that this is equivalent to 1. So QP is equal to 1, and QP is less than KP. Right, our KP value here is 81.9. So in that case, we haven't reached the equilibrium yet, and so products will be favored. So the reaction will move forward. All right, so in that case, the products will receive the plus x. So this is plus 2x, negative x, and negative x. All right, and then we plug it into the Kp expression. And our Kp value is 81.9. And because the concentration of the iodine gas and the chloride gas is the same, I can just square this. Okay. And we can simplify this further by taking the square root of both sides. And we get 9.05 here. Okay, and then we can try to solve for x. So 9.05 times 0.100 minus x. Okay, and then we get 0.805 equals 11.05x. So our x value here is 0.073. All right, and then we just plug it into the equilibrium functions. And we get concentration for I2 equals 0.1 minus this number. Same thing for Cl2, and then for ICl, that would be 0.246. All right, so these are the equilibrium concentrations. All right, so you can actually try to simplify the math by using approximations, valid approximations. So if you're given this chemical reaction equation with a value of Kc and initial concentrations, how do you find the equilibrium concentrations? All right, so you set up your ice table, you have your initial change in equilibrium, and then because you're given the value of H2S in number of moles, you would have to convert this to molarity, moles per liter. And you're given the volume of the vessel here, right, 0.5 liters. So you calculate the molarity, and we get 0.025 for the concentration of hydrogen disulfide. So you put that in this box. And then you compare QC and KC. Right, QC is less than KC, and so it'll proceed forward. So it's a forward reaction. The reactant will receive a negative sign, and then the products will get positive signs. And you do the math here, and we get these equilibrium concentrations in terms of X. And then we plug these values into the KC expression, and we get this. Right, so it looks like a very complicated algebra problem, because then you're going to get cube, right, 2x or 4x cube divided by another variable, x. And so what we can do here is we can approximate this by assuming that x is a small number. Okay, so if x is close to 0, then that minus 2x is basically 0. All right, so we can just get rid of that and solve for x, either using calculator or quadratic formula. And we get this x value, 2.97 times 10 to the negative fourth. But you still have to validate this value. Is this approximation valid, basically? And so in order to validate this, the value of x has to be less than or equal to 5%. Okay, of the initial concentration. So in order to validate this, you divide this number by the initial concentration, 0.0250, multiplied by 100%, and you get 1.19%. And so because it's less than 5%, it's considered valid. Okay. You're more than welcome to do the hard way and actually calculate for x, but it's not going to be that far away from the approximated value. Okay. All right, so once you get that value of x, then you plug it into the equilibrium constant, or equilibrium concentration in terms of x, and we get these values here for the concentrations. All right, there are some instances when the approximation is invalid. Okay, so again, we're given the same exact scenario here. The only difference is the initial concentration of hydrogen disulfide. Okay, so now it's lower than 0.250. All right, so when you divide that by 0.5, we get a value of concentration. And that concentration is 2.5 times 10 to the negative fourth, so lower than the previous example. So you do the same thing here, and we get to this point, right? When we're validating, when we're approximating the value of x. So if we treat x as small, then you can just get rid of it, right? And solve for x. So x here in this case is 1.38 times 10 to the negative 5. Divide that by the initial concentration, multiply by 100%, and see if that is a valid approximation. To me, 5.52 is not a big deal. To me, that's a valid approximation, but the book says it's invalid. So that's invalid, okay? I mean, come on, 0.005. Apparently that's invalid, and so it wouldn't be a good approximation. So what you can do is, if you get an invalid, if it's greater than 5%, then you can do another approximation, okay, according to the book. Second approximation, the book actually calls it x is small approximation, okay? That's the terminology, guys. All right, so this is where we left off from the previous slide. And so we approximate it again. What that means is you're going to plug in the value that you just determined into this x. So plug that number in, and then resolve for x. Okay, so if you plug this number in that we just calculated from the previous slide back to this x and resolve for x, then we get a new value of x. Okay, and if we validate this, we get 5.08%. Look at that. Closer to 5%, guys. And the book says this is the best approximation, because you can do the same thing. You can do it again, but it's actually going to give you a larger value if you do it the third time. So this is the best approximation. So there may be one question on the test, okay, level 5, okay, level 5 question, in which you have to validate or determine whether it's valid or not. Okay. All right, and then once you determine, or once you've validated it and it is valid, that you plug in the number to the equilibrium concentration in terms of x to get the values of the concentrations, and you get these numbers. Okay, so that's just another extra step. So I would say that's a level 5 because of that extra step. All right, so this is the last part of the chapter, right? The concept. It's LuciaToliss Principle, right? So this principle basically helps you predict which direction or the effect of changes in conditions have on the position of the equilibrium. Okay, will the equilibrium shift to the right or to the left depending on that change that you made, right? So this principle states that if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize that disturbance. Okay, so what are these disturbances? There are 3, and we're going to cover all 3. So one disturbance is the change in concentration. So if you were to change the concentration of the reactant or the product, how will we determine the shift in the equilibrium? Okay. The other disturbance is changing the volume or the pressure. And the third one is changing the temperature. And the temperature, of course, affects the equilibrium, but that will depend on the type of reaction. Is it an endothermic reaction? Is it an exothermic reaction? And how does increasing the temperature change the equilibrium. Okay, so those are the things that we're going to look at in the next few slides. All right, do you guys have any questions so far? Okay. All right, so the first one here is the effect of concentration. So what do you think would happen to the equilibrium if you were to add additional product, nitrogen dioxide? So if you're increasing the concentration of the product, how will that change, or how will that affect the equilibrium? So you can look at it in terms of Q and K.
It would push it up, right?
So your product concentration is increasing, right? So if you look at that in terms of Q, the reaction quotient, then the value of Q would be greater than the value of K, right? The equilibrium constant, because you added extra product concentration. So Q is greater than K, then the reactants are favored, so it'll shift to the left towards the product.
But I mean, like the overall levels when it's done will.
Right, the overall concentration would increase, but because we have to go back to the equilibrium state, then you have to shift the reaction towards the left, towards the reactants. Okay. All right, so you can always compare the value of Q and K. All right, so to explain that a little bit in detail, before the addition of nitrogen dioxide, Q is equal to K, which is at equilibrium, but because you added more products, the value of Q increases, making it greater than K. Okay, so the reaction has to shift to the left in order to restore that equilibrium. Same idea here. So if you were to add more reactants, then the equilibrium will shift towards the products. The products are favored. Okay, so it will shift to the right. All right, so the next slide here basically summarizes the effect of concentration on equilibrium. So if you were to decrease the concentration of the reactant, then the reaction would shift towards the reactants. Okay, so it will shift left. If you were to increase the concentration of the reactant, then it will shift right, away from the added chemicals. And if you were to increase the concentration of the product, you would shift to the left, away from the added chemical. And finally, if you were to decrease the amount of product, then it'll shift right, my right, towards the product. Okay. So to summarize this in a statement, the equilibrium shifts away from the side with added chemicals or towards the side with removed chemicals. So if you ever get stuck on this type of problem, just remember to compare Q and K. Okay, if you can't remember this statement right here, then compare Q and K. Okay. So for example, if you were to, let's say, decrease the first one here, decrease the concentration of reactant, what does that tell you about the Q value? Increases, right? Because reactant is in the denominator. So if decrease concentration of reactant, Q increases, then it becomes greater than K, and so it'll actually favor the reactant, so it will shift left. All right, let's look at an example here. We have this chemical reaction equation. What do you think is the effect of adding additional carbon dioxide to the reaction mixture? So carbon dioxide is a product, so if you were increasing the concentration of the product, which direction will the reaction go? Will shift to the left, so that's simple. What about the effect of adding additional calcium carbonate, which is a product, a reactant? So this is kind of a trick question. Remember about solids and liquids? Yeah, so they don't play any role in equilibrium. So no effect for adding additional calcium carbonate.
So, in that equation, the only thing you could affect was the gas.
Yeah.
Why didn't it say
On the
add
equilibrium.
both?
Say that again?
So that was why I didn't add, it wasn't saying both products to add some, it was just saying that.
Right, exactly. All right, so we just talked about concentration and effect on equilibrium. What about pressure, volume, and the number of moles, right? So you learn from General Chemistry 1 that if you were to increase volume, you decrease pressure, right? You decrease volume, you increase pressure. They're inversely proportional, right? And what about the relationship between number of moles and pressure? Right, they're directly related. So if you were to increase the number of moles, you also increase the pressure. Decrease the number of moles, decrease pressure. Okay. All right, so let's take a look at the effect of changing the volume, right, on the reaction or the equilibrium. So if volume was decreased, what happens to pressure? It increases. All right, so pressure increases. So because you increase pressure, you want to decrease pressure back to normal in order to restore that equilibrium, right? So how do you decrease the pressure? So how would you shift the reaction in order to decrease the pressure back to normal?
Go from products to reactants to create with that.
It would be related to the number of moles, right? So notice that on the right-hand side, the product side, you only have coefficient of 2. That means you have 2 moles of products. Versus on the left side, the reactant side, you have 4 moles of the reactants, right? And so in order to decrease that pressure back to normal, you would have to decrease the number of moles, right? So going from left to right would decrease the number of moles. So shifting from left to right, from 4 moles to 2 moles, would decrease the pressure back to normal. Does that make sense? Do I have to write that down here? So here you have 4 moles on the left-hand side. On the right-hand side, you have 2 moles. Right. So shifting the reaction from left to right would decrease the number of moles, right? From 4 to 2. There you go. So that's basically the answer. So it shifts to the right. All right, and we can do the same thing. If volume was increased, then pressure decreases, and so it has to shift from right to left in order to increase the pressure back to normal. Okay. And the last one here is temperature, the effect of temperature on equilibrium. So there are 2 types. Again, you have to look at, okay, it looks like this is a slide that summarizes what we just talked about. So I'm going to skip to these last 2 right here. All right, so if the reactants and products have equal number of moles, then there's actually no effect on the equilibrium. Changing the volume or the pressure won't have any effect on the equilibrium. Okay. And the addition of an inert gas in the system will also have no effect on the equilibrium because of the fact that you have an inert gas. Right? Inert means it's stable. It's not reacting with the chemicals in the system. All right, so I'm going to skip this part right here and move on to temperature. So the effect of temperature, you would have to look at the type of reaction. Is it an exothermic or endothermic? Because they have different effects. So if you're looking at an exothermic reaction, adding heat will actually shift the reaction to the left, away from the added heat.
Both of those say exothermic.
Huh? One is removing heat. Okay, so what was the question?
No, well, they both say exothermic, even though one says add and one says remove.
Right, I'm giving you a scenario here. So what happens if you were to increase the temperature? What happens when you decrease the temperature? Okay. So when you increase temperature, then you're adding heat, right? So when you increase temperature, you're actually shifting the reaction towards the reactants. So it's going to be a reverse reaction. And notice the value of K. You will actually get a smaller value of K, because even though the equilibrium constant is a constant, it's only constant at constant temperature. Well, that's a lot of constants in that one statement. Did you guys get that though? Okay, so the reason why it's a smaller K value is because you're shifting the reaction towards the left. You're increasing the concentration of the the reactants. Okay, and reactants in an equilibrium constant is in the denominator. So increasing the concentration of reactant will decrease the value of K. Okay, if you were to remove heat, okay, the second example here, will shift the reaction to the right towards the products, favoring the products. So if you're making more of the products, then you're increasing the value of K. And this would be the reverse for endothermic reaction. All right, here's endothermic reaction. If you were to increase temperature by adding heat, you would actually force the reaction to move away from the reactant, so towards the products. Products are favored, value of K increases. Okay, and it would be the reverse if you were to remove the heat. Right, it'll favor the reactants, increasing the concentration of reactants, giving you a smaller value of K. You guys have any questions so far? All right, let's take a look at this example here. It tells you that the reaction is endothermic. Okay? Breaking down calcium carbonate into calcium oxide and carbon dioxide is an endothermic process. So that means that heat is absorbed. What is the effect of increasing the temperature of the reaction?
Shifts it, right?
Hector, what do you think? Shifts right? Charles? Shifts right? That's right. So it shifts to the right because you're moving away from the added heat. Okay, what about decreasing the temperature? It would be the reverse, right? Towards the reactants. All right, so that ends chapter 15.